One very special type of differential equation is one that um, is related to exponential growth and decay. One example of this is if we want to see how bright, how much light passes through a certain amount of water, it turns out that it decays exponentially the further down we go. So the percent of light that decays, now we're talking about 100% being at the top of the surface, and as we go down, well, the percent that remains is what we're measuring. The percent of light decays with a constant relative growth rate. Now, what do we mean by constant relative growth rate? That means if we take the derivative of the amount of light that remains, so that's dp dt, and divide it by the amount of light that remains. So we're taking the derivative divided by the amount. So dp dt divided by p, we're going to get a constant number, and that's called the constant relative growth rate. At 2 feet, 15% of the light has been absorbed. We're going to need to find the relative growth rate and then figure out how much light makes it to a depth of 9 feet. We know the general form for an exponential function is p equals the initial amount times e to the kx, k being our constant relative growth rate. Our initial amount is 100 here because we have 100% of the light at the surface of the water, where x represents our depth. I also could have chosen the number 1 to represent 100, and that would just change over here. When I say at x equals 2, right now I'm saying p is 85 as in 85%. I could say, well, if I choose the initial amount to be 1, p would be 0.85. So it's relative. Alright, so what we'll do is we'll put these two values in, x equals 2, p equals 85, substitute those in. So 85 is 100 e to the 2k, essentially. And we want to solve for k. Divide both sides by 100 first. We get the 0.85 that we mentioned earlier. In order to solve for k, we pull out the natural logarithm. Natural log of 0.85 is 2k, so k is half of the natural log of 0.85, which is about negative 0.0813. So we've answered part A. What is our constant relative growth rate? It is a decay of 8.13%. So now we need to answer part B. What happens when we're 9 feet deep? How much light makes it? What percent? Well, there's our equation now. I've substituted the value k in because that's a constant. It will be unchanging. We'll now substitute 9 in for x. And when I put this into my calculator, I get 48.13, which means that at 9 feet, only 48.13% remains. Now, something I didn't mention earlier, just remember now, I said 15% has been absorbed. I didn't explain why I got this 85. Well, if 15% has been absorbed, only 85% still remains. So that's why I went from 15 to 85. Just something very specific for this particular equation, or for this particular problem. Well, the next one deals with something that's known as a half-life, and I'll explain what that means in a moment. We have the drug Xanax, which is used for anxiety disorders, and its half-life is 11.2 hours. We want to know how long will it take for a dose to decay to 5% of its original amount. First of all, this seems like we don't have quite enough information. We don't know what the initial amount was. We'll see that that doesn't really have a factor in things. And so the real question is, what do we mean by a half-life? Well, a half-life is how long it takes a substance to decay to half its original amount. So if I took a particular dosage of Xanax, in 11.2 hours, the amount in my system would be half of what I had originally. Actually, if I go another 11.2 hours, so to 22.4 hours, half of that half, so only 25% would remain. Well, again, since this is a half-life type problem, it's going to be an exponential function. So we'll put it in this form. A represents the initial amount. Now we don't know what that is, but we do know that when t is 11.2, we have half of what we started with, and so p is going to be 1/2 of our original amount. Now, like I said, it seems like we should know what the original amount is in order to answer this problem, but we'll see when we substitute these in, it's not going to make a difference, because we have a factor of a on each side of the equation. If I divide both sides by a I end up with 1/2 as 11e to the 11.2k. So here again, we're finding our relative growth rate. Take the natural log of both sides, divide both sides by 11.2, and we find that our relative growth rate is a decay rate of 6.19%. Okay. So that means that if I took the rate at which the drug level is changing in my body and divided it by the drug level in my body, I would end up with this negative 0.01619. So we're going to put that into our equation. We want to know when 5% remains. Again, I don't know what I started with, but I do know, well, something that represents what I started with. That's A. So 5% of A is what we're going to let P be equal to. So 0.05A equals A times that exponential expression. Again, divide both sides by A and it washes away. Take the natural log of both sides, divide by the negative 0.0619, and we find that it's about 48.4 hours until we're down to 5%. And if you think about that just sort of logically, it makes sense. If we start off with 100%, after 11.2 hours, we're down to 50%. After another 11.2 hours, we're down to 25%. We're at 22.4 hours. If I go another 11.2 hours, we're at, 33.6 hours? We take half of 25, that's 12.5. Do it again, we'll end up at somewhere in the 44.8% has, or 44.8 hours have passed. Again, if you keep cutting in half, it makes sense that this is how long it would take. So 44.4 hours to reduce to 5% of its original amount.